Okay, thank you. Thank you everyone for coming here to see me. So I will speak about a splitting algorithm for nested events. I was hoping that it can help you to understand how I can simulate some rare events and maybe use it in your project. I want to say that it's a joint work with Charles-Édouard Breuillet, Maxime Gazot, Tony Lelièvre and Mathias Rousset. And in fact, the beginning of this work was in fact 4 years ago, and it was here in CEMRACS, and so in 2013. So in fact, I will present you the end of this project, and you will see we have done a lot of work since 4 years. So what was the idea? In fact, in some industrial problem, we have this protein, for example, in biology, and we want to compute the dissociation of this molecule, so the change of conformation of the molecular. And typically, the dynamic is very fast, so you have a typical time step of this order. And you want to see some very rare event, in fact, the dissociation of the molecule. And typically, you have to wait this time to see this dissociation. So there is a bridge, there is a gap between these two scales. And the idea is to compute a numerical simulation to bridge the gap between the time scales, which is obviously not possible with direct numerical simulation. So this is associated with a rare event, and in fact in some practical case this is done by exciting the molecule with a very powerful laser. And this is very important to compute this this dissociation in order to understand the necessary energy of the molecule to change its conformation. So, what is the typical case of the problem? You have a potential and you have two minima. This is in fact two position of the molecule, two states, and the molecule wants to jump from one state to another state. But of course the dynamic is very fast, so the molecules stay very close to this minima a lot of time. You can see on these pictures that this is on this time the molecules stay in this position on the left. And after some time it jumps from another position and stay again a very long time in this position. You can see that here the dynamic is very fast because the movement between this minimum to this minimum is very fast, but the time that you have to wait is very long. And in fact, we are not interested in this part, we are only interested in this part. So you want to make some statistical description of this part, and so if you wait a very, very long time, maybe you have 1, 2, 3, 4, 5, 6 events to make your statistical description, which is not enough, of course. Okay, but this is an energetic barrier. And you can see that there is many other situations. For example, you are in this room, and there is only one door with a corridor, and you want to change the room. So the time is the same. You don't need some energy to find the door, but the door is so little that you have to spend a lot of time in this chamber to see the door and take the corridor. And when you find the corridor, you jump very rapidly to one side to the other side. So this is linked to a slow convergence of trajectorial averages. You want to make some averages on this particular part. And so the transition is very rare event. Of course, if you have some stochastic partial differential equation with some linear part and some Brownian excitation, you want to study the dynamic of the stochastic process driven by some stochastic PDEs or PDEs with some stochastic coefficient. And you want to understand the impact of the noise. So in fact, when the noise is very small, you are very close to the deterministic behavior. And when the noise is very strong, you have something which is very noisy, and maybe it will find the door very more quickly than a deterministic evolution. So we want to understand, of course, the impact of the noise, and so we want to make some statistical description of the evolution given the noise. When you add the stochastic forcing term, we speak about metastability. So you have to say in mind that the jumps are very unlikely for small noise, and for very big noise, there is a lot of jumps. Okay? But principally, the simulation is very difficult because the simulation of one trajectory is already a problem. You can think about PDE, so maybe you need 1 second or 1 minute to compute the PDE, and you want to do this 1 million times, okay, to have a statistical description. And of course, in this 1000 simulation, you want to see a very rare event, so maybe only 1 or 2 of this simulation. Okay, so the Monte Carlo procedure is not adapted to this problem. So we have to design a new algorithm to explicitly find this rare event and make some statistical description. So this is an example of simulation. So you have a box and you have something very homogeneous, and the solution wants to split in 2 areas with a red part and a blue part, and it will stay in some minimum of the energy. So this is when there is only a blue part and a red part on one side of the box. Okay, so we are in a stable state. Okay, the solution will stay a very long time in this state, and after some time it will decide to jump otherwhere. Okay, and you have again a simulation which is very noisy. So this simulation is not typical of the problem because the noise is very strong here in order to see this transition. Okay, but in fact, when you see only the deterministic solution, you see anything. Okay, the solution stays a very long time in the position. So for example, here this is the energy with respect to the time. At some time you reach some stable states. Okay, maybe the solution has reached a stable state. It will stay a very long time close to these states, and after some time this left part disappears, and you jump in another minima, and you stay a very long time close to this minimum. Okay, and you never see another thing than this minima. Okay, the simulation here is very long. You can see maybe it takes 1 day or 2 days. If you add some stronger noise, you want to see the jump. So again, this is the energy with respect to the time, but with a very stronger noise. And you can see that the solution changed its position and jumped from at least 3 metastable states up to maybe a symmetric description. And you can see, okay, that I have this minimum of energy, maybe I have another stable state, and something really maybe more stranger, a third stable state here. And what I want to say, I want to describe, this is the time spent in each minimum. So the paradigm for this behavior, in fact, is well represented by what we call the reversible stochastic gradient system. So typically you have some SZ, stochastic differential equation, in a very big dimensional space. Okay, you can think about your PDEs and some numerical scheme. So you have a big dimension, and you have a potential. So you want to minimize the energy linked to this potential, and you have this excitation with some Brownian motion, and you have this small parameter which is epsilon, which is in fact the inverse which is linked in fact to the temperature of the box. Okay, you can think that if the temperature is very high, there is a lot of noisy movement of the particle, and if the parameter is very small, this is because the temperature is very cold, and so everything is deterministic and there is no agitation of the molecule. And the problem is these 2 points. You want to compute some expectation of some functional of a trajectory. In fact, you want to compute with respect to this pi measure. This is the law of the stochastic Markov chain. Okay, you have a Markov chain in very big dimension, and you want to compute this integral. Typically, this dimension maybe it's 100 or 1000. Okay, so again, this is not accessible with Monte Carlo. If you think about some ergodic property, you can think that this quantity is in fact given by a mean in time of the trajectory, along the trajectory. But again, if you want to see that this quantity is very close to this one, you have to take t very, very long. Okay, of course you want to visit a very, very big space, so you have to wait a very long time to see that this thing is very close to this one. And more difficult things, you want to compute something, some function of all the trajectory. Okay, this is more difficult because you can't use this quantity. And you have only, again, one representation with some Monte Carlo procedure, so you put a very big number of particles, and you have the evolution of each particle, and you want to compute some empirical mean of the functional of the trajectory. And again, if this number is big enough, you can expect that this quantity is very close to this one. In fact, we know how to do this in a more efficient way, because in fact we want to see only some functional of the trajectory. So if we choose the trajectory well, it's very easy. But if you want to compute some things about all the trajectories, it's more difficult, because you don't have access to the trajectories that you want to see. This is this trajectory are jumping from one minima to the other minima. Because even with a very long simulation, or even with 1 million particles, maybe you have only 3 or 4 jumping events. Okay, so not enough to compute this quantity. So what is the idea of the numerical algorithm to bridge the gap between these two problems? You want to compute efficiently the dynamical quantities, so this part, some things of all the trajectory. And so maybe there is a lot of other procedure, but I want to present, in fact, the adaptive multilevel splitting method. So this algorithm was developed first by Serou and Goudenège, and they prove that this algorithm is well adapted for this kind of problem. There is a lot of other techniques in finite dimension. Okay, I don't give everything, but the problem is that this is really linked to the finite dimension, and our idea was to develop an algorithm which is not dependent of the dimension, because you want to compute something in a very, very high dimensional space. So we want to develop some algorithm which is independent of the dimension. Okay, it was in fact the aim of the CEMRACS project there 4 years ago. So again, you want to see these things, okay? So this jumps between the three metastable states. And you want to compute some dynamical quantities on these trajectories. So for example, I have said that you want to compute the time that you spent in the minima. So we have seen 3 minima, okay, which is in fact these 3 minima up to some rotational symmetric view. And you want to compute the time spent very close to the minima. Of course, when the noise is very strong, you stay a lot of time close to the minima, but you can visit another minima a very, very long time. But when the noise is very small, this number is very close to 100%, so you spent all the time in this event, and you have only 0 and 0 here, okay? But this is this kind of things that we want to compute. And in fact, if you know some things about the jumping event in some stochastic reversible gradient system, there is a relation which is linked the time spent with the gap of energy here, okay? There is a gap between this energy, the energy of this minima, and the energy of this minima. And in fact, the size of the jump of energy is related to the time spent in one minima and with respect to the other minima. And in fact, if you are able to compute these things, in fact, you can have these things, which is typically the quantities that the biologists want. They want this gap of energy to understand how many energy you have to put in the molecule to force the change of conformation, okay? So you compute this quantity and it gives you access to this quantity. So now I will speak about the adaptive multilevel splitting. So what was the idea? The idea is that you want to compute a jump between some area, so maybe a ball very close to some other minimum that you don't want to see. So there is an area in the physical space. And in fact, you know that you are a very, very long time in this thing. So this is, for example, one minima. And you want to reach another places, which is B. And the probability to go from this part to this part is very, very small. So you have to make a crucial assumption. So the main assumption of this work is that we have a smooth functional, which is psi. The name is the reaction coordinate. And in fact, this is something which indexes the transition from A to B. This is the sense of the nested events. You have some possibility to design, to draw some levels between A and B. You have the assumption that A is in this part where the reaction coordinate is very small, okay, less than some data given, and B is in some other part of this reaction coordinate, okay, and the big part. And you have this level, okay, this is these things. This is the location where the reaction coordinate takes the value z. And so when you see a trajectory jumping from A to B, of course you have to pass from z minus to z max, and you have to pass through all the levels. So in fact, this is possible to write that you have the time that the solution will go in A. This is a very small time, okay? The solution will reach the minimum very rapidly, okay? You will down in energy very rapidly to the minimum. And there is another time which is very, very big. This is the time that the particle will make to go in B. And you want to compute these two times, in fact. And of course, you can decide that you have the time to reach the level Z. So this is TZ1, TZ2, TZ3, etc. So the problem is there. The probability that tau B is less than tau A. This is that the particle will reach B before coming back to A. This probability is very small, okay? This is the probability to decide to go to B unless you are very close to A. This type of reaction is that we call the reactive trajectories, okay? So typically the trajectories stay a lot of time in A, okay? This is not important, I am not interested in this part, okay? This is the fluctuation very close to the minima, and after some time it decided to reach B and not coming back to A, okay? I am only interested in this red part. This is the jump from A to B. And I want to compute some things about the law of the trajectory. So this is the law of the trajectory, given that the trajectory will reach B before going back to A. Okay? And I want to make some statistical description of this law of particles. So, where are the nested events? The nested events is there. You have a sequence of levels, okay, from Z minus to Z max, and you have the nested events because you have the time to reach the level Z1. Okay, this is an event, and it is included in some other event with a level which is bigger. So you have this nested sequence of events, but this is really easy to compute this time, okay, these events, knowing these events. What is these things? You know that the particle have reached this level, and you want to compute what is the probability to reach the next level before coming back to A. Of course, all the trajectory want to go back in A, because A is some attractive point. But since if this level is very close to this level, you have a lot of chance that in fact the solution will reach the level. Okay, maybe they will go back in A with a very big probability, but maybe a lot of particles will reach these new levels. The idea is that you will split all your physical space in many levels, and if these levels are very close, this is more easy to compute each probability. And so, since you have some nested sequence of events, if you want to compute the probability to reach B before reaching A, in fact, this is only a product of all this probability. So if you keep in mind, maybe you have some Monte Carlo procedure to compute this probability and to compute this one, and this one, okay? This is more easy to obtain this probability because this is a product of not so small probability. So, since we don't want to use Monte Carlo procedure because we don't want to do a lot of simulation here, we have to design an algorithm with a very few number of particles. So what is the idea? I have the starting point on very close to A. This is on the level Z minus, okay? And you have 3 particles. This is the starting point of the trajectory. You launch the simulation, so of course all the particles want to reach A and they will not reach B, okay? This level is Z max. So all the simulation will go back in A. You compute the maximum of the reaction coordinate of the particles, okay? So you have this level, so you want to compute in fact the maximum of the trajectory. This is the point more closer to B on the trajectory. So this particle reaches maximum here, this one here, and this one here. And you decided to split the physical space with the maximum of these particles. It will be your first level. Of course, since this is the worst particle, all the particles will pass this level. So this one is only the bad one. And so, in fact, I have an idea of the probability to reach this level. In fact, this is 2 over 3. So what I do, I choose another particle. I kill this one. Okay, this is not interesting now, and I will compute the starting point on the trajectory. So there is a new starting point here or here. I choose one randomly, and I compute a new trajectory from this starting point. So this is a branching process. I have only one trajectory. I have killed this one and only branch a new trajectory on this one. So what I obtain now is again 3 trajectories starting from Z minus, but all the trajectory will reach this level. Okay, so I have now a new population of particles, but all the particles have reached this level. So I can do again the same things. I will compute the maximum of all the particles, decided which is the bad one with respect to the level, kill this one, and again branching on the other particles. in this algorithm, what I see is that at each iteration of the algorithm, all the particles will go in the direction of B. Okay, all the particles want to go in B because I'm killing the bad one. And at each time, I can compute the probability to reach the level. This is in fact only n minus 1 over n. Okay, this is the estimator of the probability. This is the 2 over 3 estimator. So the value is this one, n minus 1 over n. Okay, and I compute and do the algorithm a very big number of times, which is given by this number. This is a random number. Okay, this is the time that I need for all the particles to reach B. And so if I decided that the probability is approaching by this estimator, I can obtain, in fact, a very, very easy estimator. And this number has not to be very big. It can be 2 or 3 or 4 or 5. Okay? And so you have only a very few number of trajectories to compute. You have, of course, the number of trajectories, and at each iteration of the algorithm, you have to compute a new trajectory. So the number of trajectories, in fact, n plus q. So if these two numbers are very small, you have a very small number of trajectories to compute. Okay, this is crucial in the application because you don't have access to a lot of trajectories. So what is the quality of this estimator? The problem is that you can see, okay, this estimator is not very good. I want to compute a probability with a very small number of particles. Maybe it's not good. In fact, this estimator has a good property that we have studied in the CEMRACS 4 years ago, and we proved with the two students of the project, which was Charles-Edouard and Maxime, that this estimator is unbiased. So you don't have you have a good property for the estimator that you don't have some bias in the estimation. And second thing, you can compute something like that. Okay, you want to compute some expectation of some functional of the trajectory. Okay, this quantity, and in fact, you can define an estimator for this quantity given phi. What is the idea? You take your functional phi and you compute phi only on the last particle that you obtain. These things, this is the particles that I obtain at the iteration q. So the last iteration is at the iteration q iter, and I have an index of a number of particles. Okay, so I am a sum over all the particles, so the number of particles that I have obtained at the iteration q iter. In fact, in this algorithm, this is very clear. This is only 3. Okay, so you have an estimation of these things with only this number. So this number are given by the estimation. So this is in fact this number. So 1 minus 1 over 3 and the number of iteration. And these things, again, this is an estimator of this quantity, and again, this quantity is unbiased with respect to all the phi's that you can imagine. So you can compute what you want about the trajectories, and you obtain this quantity. What is interesting is that these trajectories, all the trajectories, they go from A to B. So of course, if this phi is computing something about the trajectories, you obtain exactly a good representation of the quantities that you are interested in. And so if you want a good statistical representation, maybe you can take 100 or 1000 particles, okay? And you obtain an estimator with a good number of trajectories. Okay, so I want to finish to convince you, but I have, again, a lot of time, so I will show you many test cases. So first test case. I have some potential indexes by some gamma. So when gamma is very high, the potential is very very smooth, and there is only two minimum. The first minimum is here, the second minimum is here. So this is the location of A, and this is the location of B. Okay, this is in dimension 2. Okay, very easy. The particles can move in the box, and of course they want to go from this place to this place. So when gamma is equal to 1, this is really easy to understand that the particles, they will go straight from A to B following this straight line. Okay, it seems quite evident. And when gamma is smaller and smaller, the shape of the potential is moving. So maybe now you want to reach A and B, but here there is a very high mountain. Okay, you can see on the isoline of the altitude, the topography of the map. And so in fact, maybe the good way to go from A to B is to choose this road here. I want to only pass, I want to avoid the maximum of the altitude, and I want to pass on this way. Okay, so I want to see this. I want to see the trajectories, and I want to see if the trajectory choose this road to pass from A to B. Okay, so what I do, I want to understand the impact of the choose of this parameter gamma, so the shape of the potential, and maybe I know that when gamma equal 1, this is quite good, and maybe when gamma is small and small, the shape of the potential maybe will be different, and maybe the particles will choose another places. I use only 100 particles, and I have a very small noise. Okay, 10 to the power minus 4. This is the size of the noise. So there is essentially the particles have some deterministic behavior, but there is a little agitation in the trajectories, and the dimension is very small. Okay, only 2, just to see some things and to draw some things. And I want to compute some reactive trajectories, so the roads that the particles are choosing. And if I want to know where the particles are choosing, I can draw some histograms of all the position on the diagonal. So here I can draw a line, and I want to see if the particles pass through the middle or pass through some location. And I want to compute where are the location of this road. Okay, so some example. When gamma equal 1, I can compute, I have a 100 reactive trajectory, so I pick one and I draw on the screen. So I'm starting from A and I'm reaching B, choosing to pass only to this way. Everywhere here it's higher, so I don't want to go higher, and I only choose this road. Of course, the deterministic behavior is to go in A. Okay, thinks about some, I don't know, maybe some movement in some valley, so you want to go back in A. But okay, I am only interested in the road starting from A and going to B. Okay, so typically the road is this one. And when gamma is equal to 1/2, there is maybe a maximum here, and there is a new road, a new possibility to go from A to B. And you can see that the particles she has choose this road. Okay, and this is very close to the deterministic road. The deterministic road is the best road that you can fix in A and fix in B. Okay, and you want to know where is the shorter road between A and B with the minimum of energy. Okay, this is typical of classical computation from optimization, and so the road is here. Again, gamma is smaller, 1/4, and now there is a new problem because there is again a maximum here. You want to go from A to B, but with the shape of the potential, there is now a new valley here, and there is a minimum. And so what is the problem? You go from A to B, and you decided to take this road. But here, there is a problem because you are in a local minimum. And so the particles want to go in B, but she doesn't know how to reach B because I have the level only to help the particles to go from A to B. And I have not the level to help the particles going from this point C to B. Okay? So the particle will stay a very, very, very long time in this place, and after she will go to B. But this is typical. The trajectory starting from A and going to B. Of course, if there is some local minimum, they will stay a very, very long time in this local minimum. Again, if I put gamma smaller and smaller, there is again there is new maximum arising in this point. So the solution will take the road here, okay, choose not to pass through the maximum, only in this road, stay a very long time, and after a new things. If gamma is smaller and smaller, there is a lot of local minima which are new in the dynamic. So in fact, this is typical of the problem that you can obtain because I have only dimension 2, okay, and I want to compute these things in dimension maybe 1,000 or 1 million. Okay, so again, in dimension 2, we have a lot of problem. But maybe this is not not a big problem. I want to compute where the particles are passing. So here, all the particles want to pass through the minimum. Okay, so this is a center. All the particles take the road at the point 0, 0, this point. Here, you can see that the particles, maybe a lot of particles take the road at the left and many particles take the road on the right. And if gamma is smaller, all the particles will go in this local minima or in this one. And you can see there is a critical bi-shape density. All the particles, they go to the left or to the right. And again, if gamma is smaller and smaller, okay, the particles, it's now impossible to take this road because this maximum is so high that maybe it's higher than everything in this box. Okay, so the particles, they don't want to choose the road at the center, and they only go to the left or to the right. More things about the computation. I can compute what I said, that the quantity which is important is to compute the time that the particles needs to go from A to B, because this is related to the energy between two metastable states. Okay, so I want to compute the times. So if I do some estimation of the time, okay, I have the time of the solution, and I want to compute this KAB. This KAB, this is the Boltzmann constant. Given some temperature, so beta is the inverse of the temperature, so there was a benchmark with another article. And so I want to compute this quantity, so the estimation of the time of the particles, and it gives me an estimation of the constant. So only with 2,000 particles and with 100,000 particles, I can obtain a good estimation of the probability, and you can see there is on the confidence interval there is not a big movement of the confidence interval, and I'm very close to the value compute by this other article into test case. Okay, so this is robust to compute some quantity. Okay, maybe another test case to show you all the other problem. Again, I have a new potential. Okay, I have this form explicitly, which was in this article, and I have two minima, and I have this local minima here, where all the particles will be trapped. And so I want to compute what is the density of the position of the particles. So of course there is a lot of particles close to A, a lot of particles close to B, and of course since all the particles are trapped in the local minima, okay, they are trapped here, and there is a big density of the particles. Okay, this is for two types of temperature. You can see that when the temperature is slower, all the particles stay a very, very long time in this well, and you can't see particles in A and B. You can compute, of course, the flux of the reactive trajectory, so where the particles want to go. So when the temperature is not big enough, all the particles starting from A, they want to go to B, and then we'll choose this road. This road is some road in the potential, and this is the location of the other minima. So all the particles will decide to choose this road. And if the temperature is changing, this is exactly the inverse. All the particles will choose to go in the local minima, and they will avoid this road. So you can see a different design of the road chosen by the particles, not given a parameter on the potential, but only given a parameter on the temperature. Okay, so this is not the same problem that in this case. Okay, because in this case I am changing the potential and the temperature is the same. But if now I don't change the potential, but I change the temperature, you have the same kind of behavior. Okay, there is in fact a competition between the shape of the potential and the temperature. Okay, maybe I will stop there. I have a lot of other things, but I have no time. So I want to do some words about the CEMRACS 2013. So I want to thank the organizer, so Nicolas, Tony, and Anthony. And thanks to all the students who works on this project, so David, and Loïc, Charles-Edouard, and Maxime, of course. I want to say that this algorithm is really well designed to compute some rare event, because you can access very, very small probability. And so this is more powerful than the Monte Carlo procedure. Maybe this is not well designed for a small probability, not so small probability, okay? But if the probability is very, very small, this is well designed. I can see you only maybe an estimation. So when the probability is of order 2 to the power -4 here, you have a good estimation of the probability with only 100 particles. Okay, so I can reach a very small probability. In fact, I can reach maybe a probability of order 10 to the power -10 or -12 with only 100 particles. Okay, so this is really well designed for very small particles. Okay, so thank you.